Okay, hello everybody. Welcome to our colloquium. So today's guest, Christoph Wiesner, comes to us from CERN. Christoph earned his PhD in 2014 from Goethe University in Frankfurt, Germany, studying high-intensity ion beams. From there, he continued on at Goethe University, where he was a research associate for a few years, and during that time also spent some time at Fermilab as a visiting scientist. Then later in 2016 became a CERN fellow in the accelerator beam transfer group, and since 2018 has been staff at CERN in the machine protection and electrical integrity group. So Christoph is a key person for responding to machine protection issues at LHC and its injectors. He's deputy chair of the restricted machine protection panel, and he's a scientific secretary of the machine protection panel and the FCCEE machine protection task force. So yeah, without further ado, Christoph, if you would please present us with your talk.
Thanks a lot. Many thanks for the kind introduction. Very happy to be here. So I talk about machine protection for the Large Hadron Collider and beyond. I give an introduction about CERN and its accelerator complex, then describe the Large Hadron Collider, focusing on two key aspects for the physics reach, which is the maximum particle energy that we can reach and the luminosity, which directly translates into challenges for the safe operation of the machine, namely the stored energy in the magnet system and the stored energy in the particle beams. And that's why we need a sophisticated quench and machine protection system. Then I talk about relevant beam failures, in particular on beam-dust interactions, and give a glimpse in the future of high luminosity LHC and FCC. So what is CERN? CERN is the world's biggest laboratory for particle physics, located near Geneva, Switzerland, founded almost or more than 70 years ago to do science for peaceful purposes. We now have 25 member states. You can see here the city of Geneva, the airport, the lake, and outlines of the main accelerators. So let's have a look at the CERN accelerator complex. Let's dive in. Let's go to Europe. Let's go to Geneva. And let's go to the Large Hadron Collider. And the first question to ask is, how do we actually get the protons into the Large Hadron Collider? And you see here an animation. It starts all with a bottle of hydrogen, where the gas goes into the ion source, is ionized, and then is accelerated in a linear accelerator to 160 mega electron volts. Then further on in the booster, which are actually 4 rings on top of each other, to 2 giga electron volts. And then further on in the proton synchrotron to 26 giga electron volts. From there, it goes into the super proton synchrotron, which is already 7 kilometers in circumference, where we accelerate the particles to 450 giga electron volts. And from the SPS, we inject into the 2 rings of the Large Hadron Collider. You can see here the animation of the collisions in the 4 interaction points. So this is an overview of the CERN accelerator complex. So first message, it's larger than the Large Hadron Collider. You see here the different machines and experiments. Do you have an idea of what percentage of the protons that we produce at CERN go into the LHC? Any guess? Sorry?
Protons out of the bottle or protons?
Let's say protons out of the booster. Or in. Yeah. I heard 1. I don't know what unit, but it's it's less than 1%. It's correct. So it's less than 1%. So it means most of the protons go to different experiments, Newton time of flight, North area experiments, and antiproton production. Nevertheless, clearly the flagship is the Large Hadron Collider, which is the most powerful accelerator ever built. We use superconducting magnets to steer two counter-rotating beams around the 27-kilometer long ring located 100 meter underground, providing a record particle energy of 2 times 6.8 TeV for collisions at 4 interaction points, where we have this gigantic detectors, Atlas, CMS, LS, LHCb. And the LHC provides a very high peak luminosity of currently 2.2 10 to the 34 per square centimeter second for Atlas CMS, which is a leveled luminosity. We could even go higher. And here you have already two key factors that determine the physics reach of the LHC, which is the particle energy, the maximum energy that we can accelerate the particles to, and the luminosity. So what limits the maximum particle energy? It is limited by our ability to keep the protons on their circular path. So if you just equate the centripetal force for a circular motion and the Lorentz force, and then you come to this equation, which is very simple and tells us that the maximum momentum or energy that you can store for a given charge state is given by the strength of the magnetic bending field and the bending radius, so the ring size. So it means for the LHC we need very powerful dipole magnets. We have 1,232 main dipole magnets, 15-meter lengths each of it, covering 2/3 of the 27-kilometer ring. A twin aperture, so the two beams are separated here, providing a nominal field of above 8 Tesla for a nominal current of almost 12,000 amps using superconducting technology, niobium titanium coils, cooled to 1.9 Kelvin. So using superfluid helium for the cooling. Maybe to note that for circular lepton machines, the energy is not limited first by the dipole strength, but before by synchronous radiation, because they emit so much synchronous radiation that you cannot come to these energies. So you can imagine with these numbers that it's a huge amount of energy stored in these magnets. The number is 7 megajoule for one dipole. And if you add it up, we have a stored energy in the magnet circuits of around 9 gigajoule, which is equivalent to the kinetic energy of an airplane going with 920 kilometers per hour. And you can melt more than 10 tons of copper with this power. And it's distributed mainly over the 8 dipole powering circuits. So this underlines that we need a very reliable, sophisticated magnet and quench protection system. And I illustrate the need with one practical example, which is the incident, I guess some of you will remember, in September 2008, which was actually a week after the first beam into the LHC. We still had to do powering tests in one sector, and during this powering test, an electric fault occurred at this current. And the result was this. So what happened is that there was a faulty electric connection between two dipoles, because they are connected in series, so you have to bring the current from one to the next. This caused local heating, and due to other non-conformities, an electric arc, which dissipated an estimated energy of 300 megajoule, vaporizing locally vacuum tubes, bellows, and perforating the enclosure of the vacuum and the helium, causing a pressure wave of 8 bar, which resulted in displacement of magnets and a damage zone over 700 meters. And 53 magnets had to be removed for repair or replacement. Beam operation could only resume a year later, November 29, in 2009, after having implemented an improved quench protection system also for the bus bars and interconnects. So clearly we need, yeah?
I just want to point out, Christoph, since I asked you earlier, that was before Christoph was involved. Not his fault.
But it clearly underlines the need for sophisticated protection system for the magnets. And I listed you here the main elements. So we want to timely detect a quench. A quench we understand as the transition of the superconductor to the normal conducting state. And we do this by monitoring the resistive voltage over the magnet coil. Then we want to trigger a beam dump, so get the beam out of the ring, switch off the power converters, and then we have quench heaters, which we discharge. And the idea is that we spread the energy dissipation over the entire magnet to avoid local hotspots. Then we switch in a dump resistor to extract the energy. And I listed you here the main hardware elements of the quench protection systems: energy extraction, heater discharge power supplies, quench detection. So no need to go into details, but you can, from the sheer number, see that we need a very reliable system. So if you have faulty detection, if you're too sensitive, your operation is compromised. Now I was talking about the magnets and the energy stored in the magnets. Let's have a look at the beams. First, I want to show a cycle of the LHC during normal beam operation. So it's a typical example of a few hours of LHC operation. What you can see in blue and red is the intensity, so the number of protons in beam 1 and beam 2, and in green, the beam energy, corresponding also to the dipole magnetic field. So first, if you have an empty machine, we inject a probe beam. So that's a very low intensity beam, and you barely see it here in intensity increase. So we never inject a high intensity beam into an empty ring for machine protection reasons, because it could be that there's an obstacle, it could be that one magnet is down, so we never do this. Once the probe beam is happily circulating, then we inject the physics beam. You see here, each of the steps is going one time, what we showed before in the video, from the LINAC through the whole accelerator chain to the LHC. And nowadays we do 20 injections in each beam with 144 bunches per beam. Yeah? Then we reach the full intensity. Then we start the energy ramp. So we accelerate the protons using the radio frequency cavities, ramp the magnetic field synchronously. When we reach top energy, 6.8 TeV, then we squeeze the beam further, so we reduce the beam size at the interaction points. We bring the beam into collision, and then we declare what we call stable beams, which means the detectors, the experiments, they can switch on and take physics data. And the optimum fill length is around 13 hours. Yeah. Then the intensity has dropped so much that it's more efficient to dump and to inject again. And the turnaround from stable beams to repeating the whole cycle and going back to stable beams is now a very optimized 2 hours. So let's talk about luminosity.
Can I ask you a quick question?
Sure.
So I was trying to do the math real quick. So you've got maybe about 10 megajoules of stored energy in the protons circulating inside the ring, and that's why you never inject a lot of protons at once?
Yeah. So I mean, circulating we have more. We'll have the numbers, but exactly. So if you would lose a full injection batch here,
Yeah.
this would cause damage. Yeah. So if this goes into a
Because the scale is like megajoules of energy.
yeah.
It might deposit into a very small spot. Is that the idea?
Yeah, so we have, I have the numbers later. We have 430 megajoules for the whole beam, and then this is about, let's say, roughly 10% of it.
Okay.
Yeah. And we have, yes?
So are there like two sets of detectors, and so they collide twice per cycle?
You mean for collisions? Yeah, we have the 4 detectors. Yeah. I mean, I can go back to repeat it. So we have the 4 detectors here. And we have, at the moment, we have 2,460 bunches. So the particles are not, it's not a continuous beam, it's bunched. And then you go around with the 2 beams, and then a certain number of the bunches, they collide in these interaction points. So let's look at the luminosity, because what you want to have in a collider, you want to produce certain events with a high rate. And this is given by the cross-section for this event, for example, producing a Higgs boson, which is given by nature, so there we can't do anything, and then by the luminosity. And luminosity is given by this formula for a bunch beam. As we have said, we have a bunch beam in the LHC, meaning we have 2,460 bunches, and currently a bunch population of 1.6 10 to the 11 protons, and these are the 430 megajoule that we have in the full beam. So the luminosity depends on the colliding bunch pairs. Then the bunch population, so the number of bunches per protons per bunch. The revolution frequency, so the time the protons come back for the next collision, which is given by the ring size. A geometric factor, which comes from the fact that we don't collide head-on to avoid parasitic encounters, but we collide with a crossing angle, and with the beam size at the collision points. So in summary, if you want a high instantaneous luminosity, you want high intensity beams, high number of bunches, high bunch population, and small beam sizes at the collision points. Yeah. And now we look at this 430 megajoule. So that's the stored energy, which is exceeding the nominal value from the LHC design report of 360 megajoule. It's equivalent to a kinetic energy of a 200-meter long train going 170 kilometers per hour, or more than 100 miles per hour. It is also equivalent to 100 kilogram of explosive, which is frightening. Think about it. Maybe even more frightening for some people is that it's also equivalent to 20 kilograms of Swiss chocolate. So now this example illustrates that it's not only the energy, but it's also the time scale of an energy release, which is the critical point. And in the LHC, it can be orders of 100 microsecond or 100 microseconds to milliseconds. So that's why it's critical. And we'll look at this a bit more in detail. But before, I want to give you an example of real beam impact. And then we come to the injection in an indirect way. So if these beam losses are in an uncontrolled way, they can cause damage to equipment. And I put here an example first from the very low energy end of the injector chain at 3 mega electron volt, where we missteered the beam onto a bellow for 14 minutes, a beam power of only 10 watts, but it nevertheless perforated the bellow, and we had to replace this vacuum equipment. Then here, that's a dedicated experiments before the LHC to determine damaged and safe beam limits, where half a megajoule roughly was shoot on a metal plate, and you see the result. So we say because you asked for the safe, we call it setup beam. So 3 10 to the 11 protons is what we call setup beam and safe. Then this is a real accident happened at the SPS, where a 2 megajoule beam was stored at the time, and a wrong tune setting was sent. I don't explain the details, but the result was that the beam became unstable. It was on a resonant and moved down, and you see here the result. So you perforated the vacuum chamber and made a hole here. So the whole dipole of the vacuum chamber had to be replaced, which is not so much an issue for a normal conducting machine as SPS, because there we talk about days of downtime, which is drastic, but in the LHC it would be order of magnitude months, because you have to warm up and cool down again. And that's another example of a dedicated damage experiment where 1.5 megajoule beam was now not on a like grazing incident, but on a frontal impact here, and causing roughly 80 centimeters of damage into a copper rod. So these are megajoules. Now, we said the whole beam is 430 megajoule. So one can ask the question, what happens if this full beam would hit somewhere? And that's not even easy to simulate and to calculate, because when the first particles, the first bunches hit the material, it will increase drastically the temperature, which leads to a pressure wave going out. And this depletes the density on the target axis. And this means you cannot do your normal calculations where you do Monte Carlo energy deposition and then you scale it up to the total number of protons. But you have to take into account that the following bunches and their particle showers will penetrate further into the material because the density is reduced. We call it hydrodynamic tunneling. So we have to couple the Monte Carlo energy deposition code and the hydrodynamic code. So a simulation can take several months to complete. So here I put simulated impact of the full beam. In this case, the parameters are for the upgrade of high luminosity LHC, so 2.2, 10 to the 11 protons. You see the density, temperature, and pressure over the radius and the length of a graphite target. So what you can see, the temperature after a few microseconds of impact reaches 9,000 Kelvin already. Then you get pressure waves reaching 2 gigapascal of amplitude, going radially outwards and moving into the target. And on the beam axis, you see a low density cavity forming, which penetrates deeper and reaches 6 meters after 18 microseconds. So interestingly, after a few microseconds, this density depletion front moves with a constant tunneling speed. So you can extrapolate to the full number of bunches. And the result is you get a tunneling range for high luminosity parameters of 30 meters into a graphite target. It would be 20 meters for LHC. So quite impressive. I hope this convinced you that we need a very good machine protection system. And I listed here first some design principles and main protection elements. So clearly the first thing you would like to do is to mitigate failures in the design phase. So every device which goes into the LHC, we study, we see what could be the impact, and maybe we can do mitigations which reduces the criticality. But sometimes you cannot avoid it. It still has a certain criticality, and then you need your protection elements. So then the next layer of protection during operation is ideally you want to detect all critical failures at the hardware level. So the equipment, so a radio frequency cavity which goes down, a power converter which trips, a magnet which goes down, and then you want to detect it and stop beam operation. The second layer would be that you look not directly on the hardware, but you look on the response on the beam parameters. And this is mainly the beam orbit, so the beam position and the beam losses. We have 400 beam position monitors around the ring and 4,000 beam loss monitors. Stopping operation here means we extract the beams. So we have in point 6 of the LHC a beam dumping system, one for each beam, and get the beam out and then inhibit further beam injection. So we achieve this with this main protection elements, equipment, beam monitoring. Then in addition, we have collimators, absorbers, which provide a passive protection against beam loss-induced energy deposition. They are mainly in point 3 and point 7 of the LHC. The beam dumping system, and then this is all linked with a highly reliable interlock system. And I will now go through a few of the systems. So first we start with this interlock system. We call it beam interlock system. And what it does, it collects the user status from all the relevant systems and then propagates the request to dump the beam to the beam dumping system. And this is a scheme. And the message is there are many systems connected. Currently, many 10,000 interlock conditions can request a beam dump. So we have, for example, connected the beam loss monitors, some beam position monitors, the access system, vacuum system as the pressure increases, the position of the collimators, the transferred feedback system, the status of the kickers, etc. So this sheer number shows you also that there's also a challenge in maintaining a high availability for the machine. So the number of false interlocks, so false readings, for example, from a sensor, that stop operation has to be minimized. So it's not about finding the safest solution, but finding the best trade-off between protection and operation. And this is the timeline. When a failure occurs, you have to detect it. For the beam loss monitors, we count 80 microseconds. Then the beam interlock system is informed of the failure and communicates this information to the beam damping system, which is in one location of the ring, and the failure can occur anywhere. Then the beam damping system waits for the right moment to dump, because you don't want to fire your extraction kickers on the circulating beam, but you wait for a moment where you have a deliberately kept free of particle gap in the circulating beam, called the Bord gap, and then you dump, and then takes another 89 microseconds, which is the revolution time, to get out the full beam. So in not counting detection time, it's around 300 microseconds, 3 turns of the LHC to get the beam out. This is the beam dumping system. So 1 per beam, that's the scheme. The circulating beam would go here around the ring. And then these are the extraction kickers, which are 15 kickers waiting to be fired. They have a 3 microsecond rise time to stay in this abort gap. The beam is deflected into scepter magnets, which then steer the beam into the dump line. But it would nevertheless be too much energy to just shoot the beam on one spot. So what we do, we actively move the beam. We paint a picture of the beam. This is a simulation of different bunches you see around the 89 microseconds. So we draw them in a 20 by 20 centimeter E-like figure to reduce the density. We call it dilution, consisting of 4 horizontal and 6 vertical kickers. And clearly you need very good controls and synchronization for all this. These are pictures of the dump line. So the extracted beam would go here, circulating beam LHC is here, and this from the extraction kickers to the dump block, which is here, it's roughly 1 kilometer of length. And then here the shielding is removed, so you can see the dump core, which consists of low density graphite, almost 8 meters long, and this is the only LHC element that is capable of absorbing the full beam. So whenever there's an issue and we have to get rid of the beam, we have to bring it to the dump system. Other important elements are the collimators. So these are movable devices which define the aperture and restrict the aperture for the circulating beam. This way they can intercept particles that are off, that are on large amplitude trajectories, and they provide passive machine protection in case of beam orbit excursions, if the beam is moving, but also clean the beam halo and reduce the background for the experiments. There are around 100 collimators installed in the LHC. You see one shown here. The beam would go here, and here this is shown like the beam view, and I put here as an illustration the beam spot which goes through, and you have to imagine that these collimators, which are typically 2 jaws which you move together, they, for some of the collimators, they have a gap of 3 millimeters or even less. So you have to imagine that here you have your beam, 430 megajoules, going with the speed of light, 11,000 times a second to these collimators. Now we want, if we have these beam losses, we want to confine them in the collimation system and not that they spread in the what we call cold region, so the region of superconducting magnets, or even in the experiments. So to reach the efficiency that we need a multi-stage cleaning. So we have primary collimators which catch the primary beam particles, then secondary collimators, shower absorbers, tertiary collimators, and only this here together leads to an efficiency of cleaning, so the number of particles that are lost and stay in this collimation region of 99.99%, so 10 to the minus 4 inefficiency. Now I come back to our chocolate and explosive, so the time scale of the energy release. So we distinguish between ultra-fast failures, slow failures, and then you can have abnormal conditions, lifetime drops, and then typical operation conditions where you have longer lifetimes of the beam. So let's start with the ultra-fast failures, which means order of 1 turn, which is again 89 microsecond. So an example is if one of the extraction kickers, but the same for the injection kickers, if they misfire, then this is so fast that you cannot react. So you have to rely on passive absorbers or procedures, like what you mentioned before, limit the injected beam intensity, because it would be too fast to react. Then you have the fast failures, which can be very critical and have to be analyzed in detail. Examples are beam-dust interactions, and I talk a bit more about this in a minute. Failure of normal conducting magnets, because they have a time constant, a small time constant, so the field decay is much faster than for the superconducting magnets, which if they quench, the time is less critical. Failure of the transverse feedback system, or beam instabilities, if the beam starts moving. So these are in the orders of hundreds of microseconds, milliseconds to seconds. And there you have to detect, ideally on the hardware side. If not, look at the beam response, mainly beam losses and beam orbit, and rely on collimators for off particles, and then dump the beam as soon as possible. Then you have other abnormal conditions which are less critical because the time scale is higher. So you can have losses if you change something in the optics, if you do parameter tuning, if you go through this full cycle and all the beam manipulations. They rely on the collimators, and we have an orbit feedback which actively brings back the beam if it's off. And I give you one example here on earthquakes. So I remember still one of the early days I was at CERN, I was in the control room, and I saw that the orbit feedback is reacting, so that the beam is brought back. And I was, what's going on? And the experienced operator, she said, this looks like an earthquake. Checking, there was an earthquake in Mexico, actually, recently. Yeah. So what happens is you have the earthquake wave going through the crust of the Earth. It reaches the LHC, and then, of course, the Earth moves. Also, the LHC moves, which is 27 kilometers. I mean, it's not a lot, but the beam sees it. And I put you even a plot here from a recent example from the earthquake in Kamchatka, Russia, in July. And you see here, this is the horizontal, because then it's mainly on the horizontal plane. You see the response. So it's not critical for us. It's not critical for machine protection because it's slow. Yeah, but it maybe gives you an idea that how complex the machine is and what you have to take into account to operate it in an efficient and safe way. By the way, we can also see the tides, the moon, because this changes the gravity, it changes, but it's of course even slower, so less critical.
What was the time scale on that previous slide? I'm sorry.
Yeah.
I can't see it.
What's the time scale on the?
Here,
Yeah.
so these are 10 minutes.
10 minutes.
So this is 2 a.m. and 4 minutes. The earthquake was roughly 40 minutes before. And this is apparently the time to reach Geneva. And then this is about 10 minutes for the.
Okay. Thank you.
So now let's have a look on beam-dust interactions, which is one of the failure cases that we have. And beam-dust interactions, they account for a large fraction of the irregular beam loss events that we have at the LHC. And they cause us some headaches. They caused 17 magnet quenches of superconducting magnets and around 180 premature early beam dumps during the run 2 and the present run of the LHC. We see a strong conditioning, so the interaction rate goes significantly down during a run, but then it jumps up after a long shutdown. For LHC, it's not a showstopper. We still have enough quench margin, so we don't have a huge amount of quenches, but it's nevertheless a downtime contributor. But if we think of the next machines, it might be critical for the performance reach of future colliders, FCC HH, for sure, but also for the Lepton Collider, FCCE. And I give you here an example of the Lepton Collider in Tsukuba, Japan, Supercake B, where the luminosity reach is very limited to events which I call sudden beam losses, which can damage collimators. You see here a picture, and pushes their intensity down so that they cannot reach their full luminosity. And they believe it's dust induced, but it's very fast. So fast means here we lose most of the beam in one turn. So you cannot react. That's why we want to understand this. So the present model that we have is you have a dust grain on our metallic beam screen, which surrounds the beam, which can be not charged or negatively pre-charged. And this dust grain enters the proton beam. And when it goes into the beam, you have several effects. Some protons might be scattered. You can produce hadronic showers, because it's like you move matter into the beam and you have this high energy protons impacting. You create you make pair production, pions, neutrons, etc., and they go out of the chamber and they can cause a magnet quench. And to keep in mind that on the beam intensity we don't see any big effect, because it's a few protons. It can be 10 to the 7, 10 to the 8 protons which are consumed here. However, 10 to the 7 protons can be sufficient to quench a magnet. And we have 4 10 to the 14 protons stored in one beam. And we have our beam loss monitors, which have a certain protection threshold, and if you exceed it, you trigger a beam dump. So I've seen before. So this can also create downtime. Also, electrons are kicked out of this dust grain, and then it gets positively ionized. And since we operate with positively charged beam particles, it will be expelled from the positive beam potential. And it's actually a relatively fast process. So you can simulate it. We have a model which numerically solves the equation of motion, and then time resolved computes the ionization rate from the escaping knock-on electrons, calculates the number of inelastic collisions. And you see here some simulated dust trajectory. So that's what Philip, who is now here for 3 months at Boulder, is doing, these kind of simulations. So you see here the beam going into the plane and the different density 1, 2, 3 sigma levels, and a simulation of a dust grain falling in, getting ionized and being expelled, and for other starting parameters. So the dust grain doesn't reach the center of the beam. It's ionized and expelled before it even reaches the center of the beam. And here I compare the nuclear collision rates observed in blue from the measurement from the beam loss monitors and this best fit simulation. And you see that we can in principle reproduce the time scale of these losses. And if you do not one comparison, but for hundreds or a few thousand of events, you can conclude that overall the measured beam losses agree well with the model if we assume that the dust grains are negatively pre-charged in this, charge to mass ratio. So this part, we have a decent understanding. However, now if you assume your dust grain is charged and it's on this metallic beam screen, we don't understand how it's charged exactly and what is the release mechanism, what lofts it off the surface. And that's one of the reasons I'm here this week, because we are collaborating with LASP to find out what the charging and release mechanisms are. And I hope you can help us to shed some light on this mystery. Now, let's take a few minutes and look into the future. First, high luminosity LHC. So with the high luminosity LHC, we want to increase the luminosity further. And you remember the formula. So for high luminosity LHC, we want to increase the bunch population to 2.2 10 to 11, so from 1.6, which we have now, to 2.2, which brings the total stored energy to 680 megajoule. Then we do an RF manipulation, radio frequency manipulation, so-called cavities, to increase the geometric factor again. And we want to reduce the beam size even more at the interaction points using new final focusing quadrupole triplets, more powerful ones, while also reducing the emittance, so increasing the beam quality from the injectors. The installation for the new equipment will start mid next year, and then we have an almost 4-year-long shutdown free to install all the equipment and then restart. And clearly, there are several challenges for machine protection: the high intensity, the stored energy of the beam, but also several new equipment which have certain tricky failure cases. So now look a bit more into the future. We are studying a future circular collider. So if you think the Large Hadron Collider is large, you can see this picture here. This would be the future circular collider, 91 kilometer in circumference in the Geneva area. And it would be a 2-stage machine. So you would start with an electron-positron collider, FCC-EE. For precision measurements, Higgs, ZW, TT bar, followed by a hadron machine in the same tunnel, which would then be a discovery machine with a reach of up to 100 tera-electron-volt center of mass. Estimated costs, 15 billion Swiss francs, so it should be around 19 billion US dollars. However, spread over 12 years, and then would be a machine which would be operated in the 2 stages for several decades. It's not decided. Decision might be taken in 2028. And to mention that there are also other options under study, like a linear collider or muon collider with a longer time scale. So from the point of view of machine protection, the challenges for FCC-EE are an enormous amount of synchronization power, 100 megawatts, which must be dissipated in a safe way. The stored beam energy in the Z mode, which is the one which has the highest stored energy, is 17.5 megajoule. So a lot, but a lot less than we have seen for LHC and high luminosity LHC. However, there are similar peak energy densities that you reach in the material as compared to the high lumi beam. And the reason is that the beam size is much smaller for the lepton beams, and the interaction behavior from the high energy electrons and protons is different. You see here the simulated beam impact on a graphite target for FCC-EE for electrons and for high luminosity LHC. Note that the scale is different. So for the electrons, the peak is located a few centimeters into the target, while for the high energy proton, it's roughly 1 meter into the target. So the total energy deposited here is much larger, but the peak energy deposition is similar. And there are certain failure cases, including the beam-dust interaction, which are under study and should be understood in detail. So for 45, this brings me to my conclusion. LHC is the most powerful particle accelerator ever constructed, provides proton-proton collisions at the unprecedented energy of 6.8 tera-electron-volt per beam, delivers an instantaneous luminosity above 2 × 10⁻³ per square centimeter second, routinely stores in the last years energies of 430 megajoule per beam. The main machine protection challenges arise from the energy stored in the magnet system and in the particle beams. Therefore, we need a sophisticated, very reliable quench and machine protection system, which is complemented with rigorous operation procedure, which I didn't go into details today. I think it's a big achievement from many people who did this before I was there, so credit to them, that so far there was no beam loss-induced damage at the LHC, thanks to the diverse redundancy of the machine protection system and vigilant experts from the different equipment groups and operation teams. It means that the beam failure scenarios have to be thoroughly studied, especially for new equipment, and future accelerators will push particle energy, particle beam intensity, so that machine protection will become even more relevant. Thank you very much for your attention. Open for questions or comments.
Christoph, do you have questions? Okay.
Do the beam dust events occur randomly around the ring, or do they have particular places that they like to occur?
Yeah, very good question, of course. So it's not uniformly distributed, so there are hotspots. Yeah. And interestingly, these hotspots, I mean, the overall UFO, we call it beam dust, let's say beam dust interaction rate goes down during a few years of run. And then we have a long shutdown of 2-3 years, and we go on, and then the dust interaction rate goes up again, and you have the same hotspots again. Yeah. In addition, you have new hotspots of locations where you open and you put a new magnet, for example, or a new beam screen, which is understandable. One hotspot that we have is in sector 3-4, where this incident happened. But there are other hotspots or regions or sectors with higher UFO rate, which are even higher than this sector. And it's one of the parts which we don't understand, and we are not sure how this conditioning and deconditioning effect occurs.
Yeah, so David and I were trying to do numbers back here and not succeeding, but this is a question. You said when you have one of these dust interactions and you dump maybe a part in 10 to the minus 7, a part in 10 to the 7 of the beam into the walls, and you get a quench. And we're just curious about the numbers on that, because if I look at things, a part in 10 to the 7 is going to be order a few joules going into the, presumably into the magnets. And I mean, what's the energy budget, on quenching a magnet?
Some tens of millijoule per square centimeter, cubic centimeter.
Okay.
So of course, then it's in its energy density. So then it depends how you distribute it, but you have enough energy to reach it. Yeah.
Okay, and it's spot heating then.
I mean, it's showers. So you have the showers are not peaked because it's hadronic showers. It's still, but you hit the coil and you heat locally the coil or over a certain region. But for a coil which is 15 meters long, it's still localized. Exactly. That's even more risky. So if you quench over the full magnet, for the magnet, it's less critical than if you have one spot, because if you don't manage to have your quench heaters in place quick enough, you might have the local hotspot and the energy is dissipated locally. So this is what you want to avoid.
Other questions? Okay. Yep.
Yeah. I mean, maybe I can rephrase what I said before. I put some emphasis that the beam is powerful, which I think is true. But now you see it's also very sensitive. Yeah. So the machine is very sensitive. It's powerful, but it's also very sensitive, and that makes it tricky.
So for these dust particles, I would imagine if I shine like some blue light or UV light on them, I can eject electrons off. So could you imagine that you just protect the beam from particles falling down by putting in a sheet of blue light that essentially says, well, you start negatively charged, but I'll just knock your electrons off, make you positively charged, and now you're repelled from the beam?
Okay, there are a few levels. First, we should understand better the mechanism, and this we hope we get some support here in Boulder. Then clearly it's a big machine.
They're spending $20 billion. In my lab, I'd be concerned, but they're spending $20 billion. Yeah, okay, sorry. We'll talk to you rather than here. But yeah, go ahead.
No. It's good. And I mean, this is basically you talk about UV light, but you have these dust grains, and you have to imagine that what you have in the accelerator. I mean, okay, I have a backup slide on the charging mechanism, but to make it simple, you have enormous amount of synchrogen photons already present. Yeah, so they are everywhere basically in the machine, and it will be much more, of course, for the lepton machine. Then you have electron clouds. Yeah. You have an enormous amount of electron, which actually gives us headaches because it has a significant heat intake on our beam screen, which we have to cool. So it's one of the limitations we have for going to higher intensity with high luminosity LHC. So it's a lot going on in there on this dust grain. You have the electrons, which will, if the electron energy is low enough, it will charge does grain negatively. If it's high enough, it might, depending on the secondary electron yield, kick out more electrons, charge it positively. And then you have the synchrotron photons, which will kick off electrons. So then it will charge it positively. And this charge balance is not trivial. I mean, in first order, you would say in a machine like LHC, you expect from the electron cloud density and synchrotron light that it's negatively charged, while in some lepton machine, you would expect it to be positively charged. But it depends on the parameters and all this.
Couple over there.
Thanks for the nice talk. As one of the people who uses the 99% of the protons that don't go to the LHC, the next time I'm on shift at 2 in the morning and we lose beam because the LHC had to abort their beam, I guess I can be angry at dust now. But I had a question about the beam dumps. I mean, they remind me a bit of, they're kind of an accidental neutrino production target in a way. How many hits can they stand? How often? What kind of maintenance? I mean, the beam is regularly dumped to them, or is that very unusual? And yeah, what kind of servicing do they need?
Let's say rough number, 2 beam dumps at top energy per day. So I mean, I told you 13 hours of optimum time, so then you would go twice a day. Maybe to mention that roughly half of the beam dumps that we have are protection dumps, and the other half are operational dumps, where we say we have intensity is low enough, we want to re-inject. So it's a significant number. Of course, now it depends when they happen. If they happen after 12 hours, it doesn't hurt a lot. If they happen in the beginning of the ramp or just in the beginning of stable beams, we lose a few hours.
I'm going to piggyback off that, and then I'll turn to John.
Question sort of following on Professor Moreno. That has to do. Okay, that has to do with the beam dump also. So you had a picture of the front entrance to the beam dump, but isn't most of the energy deposited several meters into it? So I'm wondering.
Yeah, it's.
So what does that look like? Is there a way to look at that and monitor the density?
You mean the dilution pattern?
Yeah.
Yeah. So if you look longitudinally, there's a shower buildup, as we've seen before. So that's why we have different parts of different density of graphite to basically optimize the location, because you want to dissipate the energy, but you want to do it spread out such that you don't reach too much. That's why you don't use, for example, tungsten, which would stop, but it would not withstand. So we have, I think it's 1.4 and 1.8 density for the graphite, and then the peak is in the material. And these are really important devices, and we had some issues which were actually not from the graphite itself, but also there was some motion, because you have an enclosure, and it's kept in nitrogen atmosphere, so we have to avoid the risk of graphite getting too hot, and in an inert atmosphere, so that you don't, you minimize the risk that you get some burning there, and this means you have to. It's like a vacuum enclosure, and if you have this enormous bang there, it can move, and this was analyzed, and there were leaks which were created. And now we have replaced new beam dumps with an optimized one. Because for high luminosity LHC, we have almost twice the design stored energy.
So my question's kind of related, but I'm going to unfairly ask you to speculate on the FCC-HH beam dump. At the conceptual design level, does it just scale up in size and depth, and maybe perhaps the degree of rastering of the beam across the face of the dump? Is it relatively straightforward at first order to just scale up for an FCC-HH, or is that actually likely to be a major challenge?
It's for sure a challenge. So if FCC-HH would go up to, let's say, order 8 gigajoule of stored beam energy, so if you go in this direction, you would need much more dilution. Yeah, and you can of course make it longer, lower density. So that's, let's say, the standard approach. There are also people studying if you do a liquid dump, then at least you don't have the issue that you create, that you make a hole or whatever. It's like self-repairing, but you need very long, very long terms.
Interesting. Yeah, that'd be neat. Okay, another question over there.
As probably the only chemist in the room, and certainly probably the most ignorant physicist, can you explain sort of why carbon is so good for this? I mean, is it refractory? Why is carbon chosen?
For the beam intercepting?
Yeah, for the beam dump.
Carbon is very robust. There's a high, melting temperature, but it's still a light material.
So that's the only, there's, boron's not better or whatever. It really, is it just a matter of, why wouldn't it be tungsten or something else, something other material that's very highly refractory?
As the first stage, we use this low energy, low density materials like graphite, for example, for primary collimators. And then for the shower stopping, for the tertiary collimators, for example, we use tungsten because there you want to really stop it. So it depends on what you want to do. But if you put tungsten directly in the beam, it would not survive.
Yeah. So you really need this super long, slow absorbing, if you will, material. Right?
Yeah, or you dilute it. In a way, it's a diluter. So it's not really a full absorber, what we have the collimators. And then you have the secondary and tertiary stage to really get rid of the energy.
And there's no value in, let's say, doping the tungsten with other metals or something? Maybe everything works fine with carbon. But you could dope this meter-long piece of carbon with different sorts of interesting meters, right?
Yeah.
Right. Look, I come back to James, $13 billion, right?
We are very open for suggestions. It's not easy. At the moment, we look into different also carbon materials, carbon reinforced carbon, different types of Sigraflex and graphite, etc. That's what the colleagues who work on the beam dump are studying.
Any other questions? Okay, let's thank our speaker one last time. Thank you, Christoph. Very interesting.
You're welcome. Thank you.
Thank you, everybody.